All right, so for our final example, let's take a look at how we calculate friction when we have multiple applied forces. So in this case, we have a 65 kilogram ice skater who's being pushed by two other ice skaters as shown to the right. And we're given the pushing forces here in newtons. We're also given the coefficient of kinetic friction between their skates and the ice. First, we're going to calculate the total or the net pushing force on the skater. Then, once we know essentially the resultant vector or the net force on the skater, both the magnitude and direction, we can then subtract friction from that net force. Okay, so whenever we have multiple pushes or pulls, we know that friction will oppose motion, right? But I don't know which direction this object will move in. In order to determine that, I have to figure out which direction it will accelerate in. So once I figure out the net acceleration, I can then determine which direction friction will act in, and then I can just subtract the frictional force from that net force. That's how we solve these problems. So let me go ahead and begin by solving for the net force. I will draw a force diagram. I won't draw an interaction diagram in this case. We're only evaluating the forces here from a top-down view, so I'm not thinking about the normal force or the gravitational force, although I will consider that when we get into friction. So for right now, I'm just treating this like a vector addition problem. All right, then I'll go ahead and think about the x and y components for both force 1 and force 2. Force 1 is purely x direction, so it's got a x component of 26.4 newtons. There is no y component there. And then force 2 has a y component, no x component, of 18.6 newtons. And I'll say they're both pointing in the positive direction for my vector addition. So that means then that my r, my net force essentially, instead of r, I'm going to say the net force, right? These are the x and y components. So what I can do to solve for my net force, in this case, the triangle here in the diagram does a good job of this, but essentially what we're doing is we're solving for, this is my sum of force, right? And then this is my F1, and this is my F2. Again, this is 26.4, and this is 18.6. That's my y component. So if we were to use the Pythagorean theorem now, then the net force would be equal to the square root of 26.4 squared plus 18.6 squared, which is equal to 32.3 newtons. And my direction, again, if I'm solving for this theta value here, would be tangent inverse. So I'll use tangent inverse theta is equal to tangent inverse of 18.6, the y, over the x here, which will be equal to 35.2 degrees. All right, now I know that because the net force is this much in this direction, that is the direction the skater will begin to travel in, right? They will begin to accelerate in that direction. So what I can do then is on my diagram, I'm going to show this up here in the right-hand corner. If this is the direction of the skater's motion, then this arrow, I'm going to do this in blue here so you can see it better. If this is where the skater's going, then friction will act directly opposite this, right? Friction is directly opposite motion. This will be my F sub k. So what I can do is in part B, I'm asked to calculate the skater's acceleration. Well, how am I going to do that? I need the net force on the skater, right? But in this case, that's going to be equal to the total pushing force, or the total push, which we just calculated, right? That's this 32.3 newtons minus the kinetic force of friction, right? I can treat this like my new x direction. You can actually make x whatever direction you want to. So I can say this is x, and then I don't need to worry about y. I'll say that's y. Sure, why not? But again, I'm just going to treat them like they're just opposite directions. And I can just say that I'll take this net force and subtract the frictional force from it. And then there's no problem with that. So what I need to do is solve for the magnitude of the kinetic friction force, and then I will just subtract that from the net pushing force, and that will give me my net force. Then I can divide by the skater's mass to solve for her acceleration. Let's do that. I know in this case that the force of kinetic friction, again, will be the coefficient of kinetic friction times the normal force. And if I were to draw a force diagram for the skater, ignoring the horizontal forces, just considering the vertical forces acting on the skater, I would see that there are only two, right? The normal force from the ice up and the gravitational force on the skater down, and they're equal in this case because the skater is not accelerating vertically. So then I know that Fn minus Fg, again, is may, which is equal to 0. So Fn is equal to Fg, which we know Fg is m times g. So that means that Fn is equal to 65 kilograms times 9.8 meters per second squared. That'll be equal to 637 newtons. So then that means that my frictional force here is going to be, the coefficient of kinetic friction was 0.02, right, times 637 newtons, which is equal to 12.74 newtons. And so now what I'll do is to find the net force on the skater, I will subtract this 32.3 newtons. Remember, that's my F net from earlier, right, from the pushing only, not including friction, minus this frictional force. And this is my F sub k. So that means that the net force on the skater with friction will be equal to 19.6 newtons. That's how much is left over, essentially, once we account for friction. So again, this is equal to the mass of the skater times the skater's acceleration. I'm not going to say x or y direction. It's just, we have this other direction going on. That's fine. So then that would be equal to, right, the acceleration would be this net force, this 19.6 newtons divided by the mass of the skater, which is 19.6 newtons divided by 65 kilograms, which is equal to 0.3 meters per second squared. There we have it. So to solve problems involving friction when you have multiple applied, like pushing or pulling forces, just solve for the net pushing or pulling force, just like a vector addition problem. Then calculate the magnitude of friction and subtract that from your net force from the first part. Then if you're asked for acceleration, you can use Newton's second law, like always, to solve for that as needed. So this is one part vector addition problem, and then subtracting friction from that vector addition problem to solve for your net force when we account for friction. All right, this concludes the example videos for friction. Please take a look at Canvas for practice problems to begin applying all of these skills.